Just like dot product, the cross product has two forms. So for both of them, one of the forms is in Cartesian space, where you're given x, y, and z component values. And then the other form is when you are, I guess, just given the magnitudes. And we talked about this originally. Now, this was still kind of in two space, even though it's three-dimensional. Like, if you're told it's north 70 degrees east, you're given the direction in the real world. That's still a two-dimensional direction. So then what would you have to do, like with an angle of elevation of 15 degrees or something like that, to actually take it into 3D? And so that's not something that happens very often. We were talking this morning and before class about when things like this might happen. We'll talk about that briefly, but I wouldn't overthink it, okay? So as I said before, the Cartesian versions of this and working in Cartesian space is so valuable, because when you express a vector in Cartesian space, it has magnitude and direction in the way that it's expressed. And you can compare it relative to other vectors. Whereas like this, it really doesn't. I mean, you could be given theta, but what does that mean? What's the orientation of that? If you think about two vectors, so if I'm holding up two vectors here, they exist in three space, but the angle between them is still two-dimensional. Like it's on a particular plane that they both exist in, like that slice, right, of three space. The angle is still kind of a two-dimensional angle. You can think of it that way. At any rate, there is the equation. A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between them, times this curious creature. And it looks a lot like dot product, except it's got this other thing on the end, and dot product is cos, and cross product is sine. Why do we need this? Anybody have an idea? Yeah, very good. The result of the cross product is a vector. Magnitude of A times magnitude of B times sine of an angle would just be a number. So we force it into being a vector by multiplying by this n. But what is this n? N is a unit vector that is magically in the direction that it needs to be in order to make this system work. So it's kind of bizarre, but trust me, we got to just remember that it's there, and it ends up just kind of getting in the way, but like it's not a big deal. It's not hard to work with, okay? So the n happens to be in the direction of A cross B, which is orthogonal to both. That's the direction. And the magnitude comes from the other part. Okay, so magnitude of A times magnitude of B times sine of theta is the magnitude, times this unit vector. When we took the learning goal up, we reminded ourselves what a unit vector is. And then, of course, theta, as it is with dot product, is the angle between A and B. So if somehow, which I don't know when this would happen, but if somehow you needed to know which direction the unit vector was going, because the orthogonal has only two directions. Remember, all the vectors that are orthogonal to both A and B would be collinear to each other, either pointing one way from them or the other way. Again, if I'm holding up two vectors, it's either going to point this way or that way. So which one is it? Well, we have this useful trick called the right-hand rule. And the right-hand rule, you can see, looks like this. Don't try to draw it or write it down. Don't worry about it. You don't need to know this, really. But you would hold your right hand up. You got to remember it's the right-hand rule. The left hand would do it backwards. And you think about this. Your index finger is A, the vector A. Your middle finger is vector B. And so I've got two vectors here. So the pencil will be A and the pen will be B. And if I line them up like this, my thumb points in the direction that the cross product vector would go. And we were talking about there's an application of this in like magnetic fields or something in physics, where you want to know which direction the current that's generated by a magnetic field is going. That's a different rule, but it's related or similar. This would be the same thing. If you were like, I don't know, I'm making this up. But if you're like maybe a mechanical engineer or like working in quantum mechanics or something like that, I could see that there's applications where you would have to figure out, well, which direction is this vector actually going? Like which direction is the current going, the electrical current? And that's when this would be used. When will you actually use it? I can basically guarantee you never. Mrs. Graham was telling a story about how she remembers using it on the test she wrote in high school, and the question that was asked was, if A and B is drawn like this, is the cross product of A cross B pointing out of the paper or into the paper? And you just go like this, oh, it's out of the paper. Or if you turn it around and go like this, oh, it's into the paper. Yeah, really useful trick. If any of you actually do it, come back and tell me what you use it for. I'd love to hear. It's pretty easy to learn. We'll never ask you about this, so you don't have to worry about it. Also, I think it's interesting that they do it with the index finger and the middle finger, but I find that really awkward. Whereas I think it still works if your thumb is A, right, and your index is B, and you've got that, then you can do it like this too. Maybe there's a reason why they don't do it like this. Maybe, I don't know. Maybe that's inappropriate. Anyway, so the right-hand rule, you don't need to know it, but it turns out that when you're not dealing in Cartesian vectors, you wouldn't know what direction it's going. Okay? Okay, so we're going to use, so that's how you can figure it out. But it's useless to us. So here we are. These are the kinds of questions we're going to be asked. Given some values, determine A cross B. The hardest part about this is remembering vector n. People will just forget it because it seems irrelevant. But, you know, it's one of those technicalities that we want to remember it. So that is 70 times 68. Get your calculator out. Try it. Sine of 50 times vector n. Again, calculator in degrees. So if you forget n in your answer, you're going to forget that. It should be there all the way, obviously, for consistency. But if you only had the value of that, then, I mean, technically it's wrong because the result of the cross product has to be vector, and vector n turns it into a vector. Any questions? And just as a reminder, a little bit of review, and so we can again compare how these are similar but different. What about A dot B? So this is vector A times vector B times cosine of the angle between them. Dot product is a scalar, so no vector n required. Again, calculator in degrees. And I got 3059.7. We know a lot about sine and cosine. If 50, if this continues to get bigger, this will get smaller. But like sine of 50 gets bigger, cosine of 50 gets smaller. So the dot product gets smaller, but the cross product gets bigger, right? Does that make sense? Like you could think that through and make sense of that. And if 50 was getting smaller, if it was going to 0, this would be getting smaller because the sine of 50 would be getting smaller. Cosine of 50 would be getting bigger. This would be getting bigger. And we know that when theta is 0, this is as big as it can be. What if it was 45? They would be, somebody said it, I thought? No? The same magnitude at least, right? Because sine of 45 and cos of 45 are the same. Kind of interesting, at 45, they'd be the same. Anyway, that's that. Okay, so that's one of the ways that you can use cross product. Another way that is interesting, surprising maybe, I'll show you a little bit of why this works out. There's a even better reason in linear algebra of why this works, but we can't get into that. But if you take linear algebra, hopefully you will. I promised you that I would post the video series. I haven't, only because the notation is different enough that I don't want people to get confused while we're working with it. So I will post it either next unit, or maybe I'll even wait till the end of next unit. You can watch it while you're doing exam review or in the summer or something like that. I would encourage you, if you're taking linear algebra, to watch it at some point. Bookmark it and watch it later if you find out you have to take linear algebra. It's really, really useful way of visualizing what linear algebra is actually talking about. It talks all about vectors, everything. It's fantastic. And I think that there's a better explanation of this in terms of linear algebra. But I have a pretty good one, but it looks like it's just a fluke. It's not a fluke, but it looks like a fluke, why it works. So strangely or surprisingly, the magnitude of A cross B, or magnitude A cross B, is the area of the parallelogram defined by vector A and vector B if they're arranged tail to tail. What does that mean? Well, again, remember what I said. If you have two vectors that exist in 3 space, because cross product only works in 3 space. If you have two vectors that are in 3 space, but you think of the sort of plane that, or the slice that they share, okay, and they have an angle between them, well, they define a parallelogram, which is a 2-dimensional figure. How does that work? Well, it works like this. I'll call this vector A, and I'll call this vector B. And so if I take vector B and I think of bringing it up here as well, and if I take vector A and think about bringing it over here as well, you can see how these two vectors define kind of a parallelogram if we project them both across each other, kind of thing. Does that make sense? And this is the area of the parallelogram. And the area of this parallelogram is equal to the magnitude of A cross B, which is obviously a scalar. Surprising? Seems bizarre, doesn't it? Possibly. But it actually makes a lot of sense. So if I redo this parallelogram over here, no, I've swapped colors, but that's okay. Okay, we okay with this so far? So this is theta. And we're talking sine in cross product. So how does that work? Well, I've got to do a right triangle. So if I bring this altitude from the tip of A down at a right angle to B, and I'm going to call this H, then sine theta is opposite over hypotenuse, which is H, over the magnitude of A. Are we okay with this? Which means H equals A times the magnitude of A, times sine theta. Right? And what is area of a parallelogram? Base times height, where height is at a right angle to the base. Now the base, this is like the measurement base, not vector B, but it happens to be the magnitude of vector B, times H, which we just saw as magnitude of A, times sine theta. And that is the magnitude of A cross B or B cross A. The magnitudes are the same. The directions are different. A cross B does not equal B cross A, but their magnitudes are equal, right? So you can kind of see how this makes sense, that the sine, that the magnitude of A times the sine gives me this. When I multiply that by the magnitude of this, it gives me the area of the parallelogram. But it looks like it just happens to be that way, but there's sort of another good reason why the cross product is defined this way. But we don't have to worry about that, okay? We got to know that property, though. That's a property that we're going to ask you about. Yeah.
What happened to the vector n?
This is magnitude. because area is just a value, right? So when we take the magnitude, we're going to actually see that happen in another example, so that might better answer your question. But this is talking about magnitude, which is a scalar, so we don't have to worry about the direction. So this is in vector space, so we're going to use the vector form, but it says find the area of the parallelogram they form when tail to tail. In other words, take the dot product, or the cross product. So a reminder of how you do A cross B from yesterday. You do Y, then Z, then X, then Y. Start with the first one on top, the second one on bottom. So the Y value of A is 3, Z is 2, X is 6, Y again 3. For B, Y is 3, Z is 9, X is -5, Y is 3 again. Cross product is a vector. On a test, if you do this wrong, or if you just leave square brackets out entirely, also wrong, just bad form. Vectors, like points, have to have the correct brackets around them. So this is 3 times 9, which is 27, minus 3 times 2, which is 6. This is 2 times -5, which is -10, minus 9 times 6, which is 54. And this is 18. 6 times 3 is 18, minus -15, so plus 15. Which is 21, -64, 33. What do we do next? We're finding the area of the parallelogram. Seema? Find the magnitude. (21 squared plus -64 squared plus 33 squared). I wonder, a couple people, when they did this on the learning goal, got it wrong. I wonder if they didn't have the negative in brackets and then ended up subtracting. These should always be positive, right? So watch, that's a silly little mistake. We know that when we're doing something like this, similar to Pythagorean theorem, those values are always squared, so they're always positive inside there, right? And it turns out this is 5,626. You might have to round this. You might give exact. This is not an area. This is a magnitude of the cross product. So I would have to finish this with the therefore statement to like answer the actual question. Don't leave it like that, right? Therefore, the area of the parallelogram is root 5626 units squared. Okay? Yes. Okay, another last parallelogram example. And this is given in the other form, where we're just given the magnitudes and given theta. So using the other formula, this one works out to approximately 749.9 times vector n. Okay, so just like the last one, we need the magnitude of this. So the area equals the magnitude of A cross B, which is the magnitude of 749.9 times vector n. But how in the world am I going to calculate that? Why?
Because the vector part.
Okay. Okay.
N is a unit vector.
N's a unit vector. Its unit is 1. This is a scalar. When I multiply through, I'll still get the same thing. And I told you that this is the magnitude of the cross product. N doesn't impact the magnitude. We get that from this part because n is a unit vector. N only needs to give us direction. But your steps would have to show n all the way through, and then you wouldn't have to show this step. But this is what's happening. So in our note as a reminder that this is what it would be, right? Which is just 749.9 units squared. Parallelogram property, don't forget it. One more property. Turns out there's another useful property of the cross product. What happens if the dot product is 0? If A dot B is 0? They're perpendicular or orthogonal, right? It says it right down here as a little reminder, if you didn't notice. So it turns out, if two vectors are collinear, their cross product will be 0. So isn't that useful? Now we can test and see if two vectors are orthogonal or if they are collinear. Previously to this, how would you have tested if they're collinear? I think you would have just looked to see if one was a scalar multiple of the other. Like proportionally speaking, are they all the same scalar multiple, all the different parts? I would say the better way of doing it is by taking the cross product, now that we know this property. It's an if and only if statement, which means if you take the cross product and get 0, then they are collinear, assuming neither of them are the 0 vector. That changes things. And if A and B are collinear, their cross product will be 0, right? That's what the if and only if means, goes both ways. So let's use this. Once given A and some constant, prove that A cross Ka is 0. So when I take A and multiply by a constant, a scalar, they will be collinear. That's almost the definition of what collinear is, right? Scalar multiple of each other. So this has to be true. Let's show it with this example. So to find Ka first, we do -3 times 4, which is -12. 1 times 4, which is 4, and 4 times 4, which is 16. And whether I do A cross Ka or the other way around, Ka cross A, be the same thing. But this tells me to do A cross Ka, so I'm going to do that. So again, writing these out, A is 1, 4, -3, 1, and K is 4, 16, -12, 4. And folks, I think if you look, you'll see why when one is a scalar multiple of the other, their cross products will add to 0. Because when I do 1 times 16, I get 16. When I do 4 times 4, I also get 16. And like that's always just going to work out. I mean, it's kind of how it has to work out, right? But that's what happens. Because one's a scalar multiple of the other, you always get something minus itself. So this is -48 plus 48 minus -48, and -12 plus 12. And by the way, it's not 0. If I said 0, I was kind of wrong. It's the 0 vector. So the magnitude is 0, but it also has no direction. Technically speaking, it's the 0 vector. So don't say equals 0 equals the 0 vector because the cross product is a vector. And it has to be, people were wondering about this and like, I don't understand what's the difference between 0 and 0 vector. But hopefully now you know that, like, for consistency, if the cross product results in a vector, it's got to result in a vector. It can't be the scalar 0. It's got to be a vector. So we need the 0 vector to be a vector. Any questions about that? There's a good chance you'll be asked, determine if these two vectors are collinear, orthogonal, or neither. And you have to know that you're putting them through the tests. Cross product for collinear, dot product for orthogonal. If it's neither, then it's neither. Okay, example 5 is a little bit different. This is the kind that we've been talking about. We haven't done one together. So here's what I want you to do. There's 3 examples here. And this is the kind where you are checking to see if this is a question that makes sense. If you went through the steps. If you knew K and A, B, C vectors or A, B, C, D vectors, and you were doing them, would you get a meaningful result or would you get something that's not possible? Here's how I want you to do this. I want you to try to do it yourself. So start with A. You can just do A for now. See if you can come up with an answer. And then when I tell you, you're going to share your answer with somebody that you're sitting close to and just briefly discuss it. Why you think it's the case. You want an answer and you want to be able to defend it, to explain it. And then we'll take it up as a class. Okay, so take a minute, hopefully only, to do A. And I've said this before, this is probably how this question would be asked. Classify each of the following. The result would be a vector, would it be a scalar, or is it not possible? So that's what you're trying to do. How many people are done A? Okay, so I want you to turn and talk in a group of 2 or 3 and see what you come up with. And if you didn't get it, then listen to what the other person says and see if it makes sense and you can challenge them or defend it. Okay, what did people done talking? What did we come up with? You think a scalar? Why? Okay, good. So here's a way you could show it, or here's a way if you had a long one, you could work through your thinking and keep track of things, because I haven't shown you notation. This is informal notation, right? These would be 1-mark questions kind of thing. But K, we have to do it in order of operations. So a scalar times a vector, the result is what? A vector. Cross with a vector. By the way, this means cross product. If all of a sudden one of these became a scalar, it doesn't change to mean multiply. It means cross product. Okay, so it doesn't mean times. Dot a vector. Vector cross vector means, or sorry, results in. This is what we just did. A vector. Yeah, good. So this is a vector. I'm going to come back to that though. Dot vector, and the dot product results in a scalar. So very good if you said scalar. I agree. This one should result in a scalar. And that's kind of how you could walk your way through it. But you see how somebody said, well, this is the dot product and it results in a scalar, so that's fine. Well, hold on. I mean, you're right. As long as this is a vector. What if I ended up with a scalar dot a vector? Not possible. That does not turn into just multiply. You can do scalar multiplication, but this means dot product. You can't take the dot product of a scalar and a vector. So this would not be possible. But because this worked out to a vector inside the brackets, it's possible, and the result is a scalar.
What if you know, like the out of mass operation is just possible?
If you're comfortable with that, I don't know how you could because, well, unless, yeah, then you could say not possible. If you're sure and you're convinced, then these are 1 mark questions. You can say whatever you want. Yep.
So if on a test, if you want us to get 0.
You could, or you could just say scalar. Yeah, but this is useful. Okay, try B. I'm going to give you a minute to finish B if you haven't done B. Okay, if you're done B, turn and talk to somebody close by and see what they came up with. See what you came up with. But it's cross. This is what I mean. Like, some people would think, well, because this is a scalar, that must now mean times. No, it still means cross. Okay, what do we come up with for B? Who can share? Who can explain? You think not possible? How come?
You multiply when A cross product of B equals a vector, and then you got a vector vector, so it still works out. Like a vector dot product of another vector equals scalar.
Yes, good. Okay, let me stay caught up here. So A cross B is a vector. Vector dot vector is fine, and it's a scalar.
But then you can't take scalar and vector.
So this is where this does not magically become multiplying or times or something like that. It's still cross product. You cannot do the cross product of a scalar and a vector, so this is not possible. Good? Okay, take a moment and do C if you haven't. Okay, turn and talk if you haven't already. What'd you come up with? What do we think? Not possible. How come? Okay, but what's the rest of the process? How does the first steps go? Go ahead, Marian.
Vector A minus vector B equals vector.
Good. So this is a scalar times a vector.
Scalar times a
Oops.
vector equals a vector.
Good.
The bottom, the other
This is an operation that's not defined, not possible, or not defined. It could be that you could define division of two vectors, define it in some meaningful way, but it's just not for us. So it looks like that's a thing that should be perfectly fine, but it's not. You cannot divide a vector by a vector, just like you can't multiply a vector by a vector. What's the reciprocal of a vector? Like, none of that makes any sense. It's just not. It's just stuff that's not defined. Okay? Good. I think we're getting the hang of that. There are the practice questions that I want you to try. The rest of the worksheet from yesterday, if you didn't do the rest of it, you can do all of it now.